we ended up taking all of the measurements for the parallel circuits for our experiment. So today we're going to be completing the conclusions drawn from the experiment, and then I'm going to go over chemistry naming conventions. So that's what we're going to be doing today. So first, let's recap our experiment quickly. We built some circuits first with bulbs connected in series. So we had 3 light bulbs connected in series, and we took the current through the circuits and then the voltage across all of the bulbs. And then we did the same for parallel circuits, connecting 3 bulbs in parallel, took the current through each of the branches, the voltage over all of the components. Okay. So our first lesson, we took the measurements for the series and we drew some conclusions. And then last week, we took the measurements for the parallel circuits, but we didn't get to the point where we can actually draw conclusions. Okay, so if you guys are stuck and you have no idea what's going on, please let me know. I do have the circuits next to me, so if you want me to take a measurement again so that you can see what it does, let me know. So essentially, this is our parallel circuit. So first we had 1 bulb in parallel, then 2 bulbs, and then 3 bulbs. And every single time we measured the voltage across the battery, and then we measured the voltage across the light bulbs. So here it was just 1 light bulb, here it was 2 light bulbs, and so forth. And then we measured the current going through the main circuit, and then the current going through each of the light bulbs. Okay, so let's start. So let's look at our table here, and our question says, what did you notice about the voltage across the battery? Okay, there was a quick question that came in. When in the course will you be doing this? This is part of the electricity part of the course, though it doesn't have an experiment set out like this. I did want to do the experiment because it helps to show you guys how to use a multimeter, how to set up the things, and then how to look at the data and draw conclusions. You guys do need to know what happens to the current and the voltage in series and parallel circuits, since they are actually in your books. So this is essentially an extension of that. Okay, continuing on. What did you notice about the voltage across the battery? So it tended to get just slightly less for the 3 bulbs, but mostly it stayed relatively the same. So the voltage is the potential that that battery will have to do some work in the circuit. Okay. What did you notice about the current through the main circuit? Okay, so our current through the main circuit dramatically increased. Here it was 400 milliamps, there it was 270 milliamps, and here it was 150 or 148 milliamps. Okay. So we need to go fill these in. So let me just grab a writing implement. So what did you notice about the voltage across the battery? It got slightly less. Okay. So what did you notice about the current through the main circuit? It increased as we added more bulbs. Okay. So that was the current, that was the voltage. So now we get to the crucial part here. What did you notice about the voltage across the bulbs? Okay, so let's look here. Here, the voltage is supposed to be pretty much the same. I don't know what the difference in measurement here is. Probably the resistance in the wires that we get. So here we look at the voltage across the bulbs. Here the voltage is pretty much the same between the 2 over here. And if we look over here, the voltage is again pretty much the same between the 3 bulbs. So the voltage stays the same across the 3 across the bulbs. Okay. So what did you notice about the current through the bulbs? Okay. So here, if you look over here, you can see here it was 148 and it stayed 148 going through the bulb. Here we had 270 and it divided itself pretty neatly across the two bulbs that we had. Here we had 400 and it divided itself fairly neatly across the three bulbs that we had. So the current gets divided amongst the branches of the parallel connections. Okay, so what did you notice about the current through the bulbs? Okay. So now we need to fill in the following over here. So in a series circuit, the what gets divided across the bulbs. Okay, so we need to go back to our series circuit. And since that was 2 weeks ago, let's quickly read through it. So here you could see the voltage across the bulb stayed pretty much the same. And our current was just the current through the main circuit. So here you could see that our voltage across the bulb, here we had 2.88 volts across the battery, but it got divided fairly evenly across the bulbs. And here, this got divided fairly evenly across the bulbs. So in a series circuit, the voltage gets divided across the bulbs, and in a parallel circuit, the current gets divided across the bulbs. So that is our conclusions that we can draw from this experiment. So what does this mean? If you think about your electricity at home and you take something with a 2-point plug, it can be a 3-point, but 2-point works for this fairly well, and you go and plug it into the wall. What happens is you are essentially plugging in a branch of a parallel circuit. And that is a good thing because you want to keep the current going through whatever device you are using fairly low, but you still want the potential from the voltage to be there to actually do the things that you want to do. So every single time you're plugging in a device, you're literally just adding a branch into the big parallel circuit, which is your entire house. So that's how that works. Using parallel connections instead of series connections for all of the things in your house is a very good thing because it keeps the current low, and the current is the thing that gives you essentially heart attacks if you get an electric shock. The voltage is fairly severe, but the current is the thing that essentially kills. So you want to keep the current low and the voltage high so that you can still do the things that you want to do. The current is also what can start fires, so you want to keep that fairly low. So that is how your house works. Your house is literally a ton of parallel circuits, and every single time you plug something in, you're just adding a branch to the parallel circuit. Okay, so that is what this experiment means. We do still use series circuits every now and then. For example, Christmas lights. Christmas lights are normally connected in series because they're very low resistance bulbs, and it's much easier to just connect them using one wire going straight through than to add each of them in parallel branches. Okay, so we do still get series circuits in the house, like in Christmas lights, but we tend to try to avoid those for safety reasons. Otherwise, I am going to continue on with chemistry naming conventions. So this is technically a topic in the F1 course, but you guys do need to know this, especially when it comes to the naming of acids. So this is the naming of acids, and I want to go through the previous kinds of things that you would have to have known from coming from Foundation 1 onwards. I'm not going to spend too much time on this, but since you do need to know the naming conventions of acids, I figured it's a good idea to go through the naming conventions of everything, either as review or as new information that you didn't know before. So let's go. So I just need something I can write with over here. Okay. So chemical naming conventions. Firstly, we get some prefixes. So we're looking essentially at the words that substance is made out of. So firstly, we get some prefixes. Mono means 1, di means 2, tri means 3. We tend to get these sorts of things in things like carbon monoxide, which is CO. You don't need to know the formulas. I'm putting them here so you can see what's happening. Okay. You don't need to know these symbols. You guys need to work on the words. I am putting these here so that it makes sense. You can see what's happening. You can see the numbers changing as we go on. You don't need to know these. Okay. So carbon monoxide is 1 carbon molecule combined with 1 oxygen molecule. That's the monoxide over there. It means 1 oxygen molecule. Carbon dioxide means 2 oxygen molecules. And then sulfur trioxide will be in 3 oxygen molecules. We get all sorts of different things. There's tetraiodide, which means 4 iodine molecules, atoms. Sulfur hexafluoride, 6 fluoride atoms. Sulfur hexafluoride, by the way, is the gas that people use on YouTube to get that very deep voice. You get helium for the high voices and then sulfur hexafluoride for the very deep voice things. So very interesting to note. So in F1, you guys need to know those 3. And I believe at one point in the F2 course, something with tetra is referenced. So you guys just need to know those. You don't need to go up to penta, hexa, hepta, and so forth. If you do get across them, you just know what they mean, which is great. In general, we don't use these kinds of prefixes when we talk about metals. We don't get for example, dihydrogen monoxide. Hydrogen is considered both a metal and a non-metal. We tend to not use something like that. So here we get to ionic compounds. So ionic compounds is a way of atoms combining together to form a compound or a molecule. So ionic compounds, like salt, we have sodium chloride. So what happens is each of them, the sodium will give off an electron, making it slightly positively charged, and the chlorine atom will then take in a electron to make it slightly negatively charged. And because they're positively charged and negatively charged, they will be attracted to each other and then will stick together in one molecule. So this is how this works. So we tend to give names to the negative ion. So here we've got sodium chloride. That means that the chlorine is our negative ion that we are using. Okay. So then if we talk about transition metals, those are the ones in the middle section of a periodic table. We need to be careful because they can have more than one charge. We tend to write them. So here we've got iron with a 3+ charge and iron with a 2+ charge. So we can call them iron 3 oxide or iron 2 oxide. This is the standard way of naming them. In older days, before this way of naming them, they used something like this: ferric oxide and ferrous oxide. So the us would mean it's got a smaller charge and the ic would mean it's got a bigger charge. So if you do come across things with this suffix in the middle of the compound, then you know it's just to do with transition metals and that refers to their charge. Okay, so some people still use these. Most of the world do not anymore because they were slightly confusing. Okay, so now we get to the different names that we get for negative ions. So if we have our negative ion and it bonds with oxygen, then its charge tends to stay the same. And what we end up getting is just different names for the same sort of thing with the same sort of charge, but it's now bonded with lots of oxygens. Okay, so here we are in group 7 of the periodic table. That is the group just before the noble gases, which means they only need one electron to look like a noble gas, and so they will only absorb one electron to become a negatively charged ion with one negative charge. Okay, so with our just standard atom over here, our standard ion, we end up with the suffix "hide" or "ide." So we've got fluoride over here, and that's just the F symbol with a minus. So again, you guys don't need to know these things, and you guys only need to know the names up to, I think, about chlorine. Something along those lines, yeah. But really, it's not a lot. So anyway, so just the one atom gives it the "ide" suffix. Then if it absorbs one oxygen atom, we've got the same charge, but now it gets hypo and ite. So we've got hypofluorite. Then if it has 2 oxygen molecules, we get ite, so fluorite. 3, we get fluorate. And then 4, we get per and 8. So we've got perfluorate. So that means we've got 4. So these hypo and per comes from hypo and hyper. Hyper meaning too many and hypo meaning too few in terms of the prefixes and suffixes. So group 7 is the only one that has 4 different possibilities. In general, we've only got 2, the ite and ate. So if you see ite and if you see ate, that just means that the ite has less oxygen atoms binded to it than the ate does. So I am telling you guys this, it will make sense in a bit. Okay, so then we get to group 6. So group 6 is 2 away from group 8, which is our noble gases. So it will absorb 2 electrons to get a charge of -2. So again, we've got ide for just the single one. Then we've got ite for 3 oxygens and 8 for 4 oxygens. So we've got sulfide, sulfite, and sulfate. So if you end up finding something with ite and 8, you'll know in terms of group 6, it's got 3 and 4 oxygen molecules. In terms of group 7, we've got the 4 possibilities up there. So we'll get to those. And there's lots of different naming conventions. I wrote these here so that you can see the way the suffixes carry through. So you guys need to know ide, ite, and 8. So now we get to group 5, which has a charge of -3. So it's 3 away from the noble gases. So it'll absorb 3 electrons to go look like the noble gases. So we've got ide, we've got ite, and we've got 8. And again, they've got this 3 and this 4. The only difference between this and group 6 over here is this charge of 3-. So here we can get things like phosphide, phosphite, phosphate. Okay, there's a bunch of examples. So we have sodium nitrate, sodium sulfate, all of these things, calcium chloride, potassium phosphate. We do get some strange ones, like here we've got ammonium phosphate. Ammonium is this special part here, that NH4. It is a special type of ion, which is a compound ion, and they tend to have special names besides the ones like phosphate and all of those. These are just binding with oxygen. They're very standard. So ammonium is a special one. You guys don't need to know its symbols. You guys, if you do come across it, you just now know what it means. We get also things like magnesium cyanide. Cyanide is a negative ion, and it's also a fairly special one in the sense that it has its own name, because it's not a normal conventional binding with oxygen. So that's what they look like. So if you see these strange things like ammonium and like cyanide, don't worry, it's just different kinds of ions. Okay. Here we get to the bit that you guys do need to know this year. Okay, the previous things was from Foundation 1 phase. This is now solely in Foundation 2. Okay, you guys will still need to know the Foundation 1 things because it is fairly relevant. But here we go. Foundation 2 stuff now. The naming of acids. So here we've got three possibilities. We've got if it ends in an "ite," if it ends in an "ate," and if it ends in an "ide." So if it ends in an "ite," it changes to "us." So we had a sulfite ion over here. So here we've got sulfurous acid. It just means that it binds with lots of hydrogens on the other side to form an acid. All acids, by the way, have this H in the front, and that is how we know they're acids, just from looking at their symbols over here. Again, you guys don't need to know the symbols. I'm putting them there for interest's sake, and so that you can see what is busy happening. Okay, so "ite" becomes "us." So sulfite becomes sulfurous acid. The "ate" becomes "ic." So we had a sulfate over here, so it becomes sulfuric acid. So again, you can see the difference here. They're essentially sulfur with some oxygen atoms, but here we've got sulfurous atoms, acid, and here we've got sulfuric acid. Okay, if it has the "ide," then it becomes hydro and ic. So the "ide," over here we had chloride, becomes hydrochloric acid. Okay, there are a few exceptions. For example, acetic acid is an organic acid, and so it follows the organic naming conventions and the organic ways of writing it. You'll see it doesn't start with an H. It is still an acid, and the reason for this is that all organic molecules follow different naming rules because they look very, very different from normal molecules, which is our ionic bonds over here. Organic compounds, different naming rules. So you guys do not need to know the organic compounds naming rules at all at this level. I've got a few over here just so that you can hear them, and so that if you look on the back end of your toothpaste or your shampoo bottle, you at least have some idea of what these things mean. So if it ends in an "ol," it means it's an alcohol. If it ends in an "08," it's some kind of scent. It's an ester. It's a scent molecule. If it ends in an "one," it's a ketone. They are specific kinds of organic molecules, and they bind in specific ways. So if it's an YL over here, then it's a chain of carbons sort of inserted in here. For example, you can get sodium sulfate. Oy, I am writing terribly, sulfate. And then you can get a chain of carbons added to it, which will give us sodium lauryl sulfate. Okay, the "ill" just tells it that there is a chain of carbons added into it. And the "lor" part over here tells us how many carbons there are. For example, this one has 12. So sodium sulfate is a fairly normal compound that we can get every day. Sodium lauryl sulfate is a kind of soap that we can use. But now you know what that essentially means. And then if we have something called ane, ene, or ine, that refers to its main chain of carbons. This YL refers to a chain of carbons that was inserted into a normal molecule. So you guys don't need to know the organic things. They're there just for interest's sake. You guys do need to know the naming conventions of acids. They are fairly important. And then from F1, you guys need to know where these suffixes come from. And then just the first four of the prefixes, which is the mono, di, tri, and tetra. That's it. Okay. So just to recap, the "ite" becomes "us," so sulfite becomes sulfurous acid, the sulfate becomes sulfuric acid, and chloride becomes hydrochloric acid. And that's that.